Okay, good morning, everyone. Welcome to the second session of the day. I hope your NDC experience has been great so far. Thank you for coming. So my name is Galiya Warrier, and you're here for a talk about little ponies and a bit of deep learning. Actually, the other way around, but. So like I said, my name is Galiya Warrier. I work for Microsoft. I'm a senior software engineer in a team called Commercial Software Engineering, where we work with enterprise customer building the projects. But today I'm going to be talking about my own personal challenge. And how many of you have young kids or nephews and nieces under age of 7, 8, 10, I don't know, something like this? Right, okay, so you will relate to this very well. So this is my daughter, Maya. So she's 5 years old. She's at school now in London. So she loves little ponies, and I'm sure you can relate to similar experiences. And if you've seen that, there's so many ponies. And I grew up in Russia, so actually I've never watched that cartoon before. So some people did, here and in the UK. But for me, it's like a brand new experience. And when she wants to talk to me about her favorite, characters and this pony did this and all that, and I was like, I have no idea who they are. So I need to learn them somehow. I need to have this meaningful conversation with my little one, right? So. Obviously, growth mindset, I can go and learn and kind of spend a bit of time, but nobody has time for that. So I work for Microsoft, so I was like, okay, let me see if I can use some of this tech and actually build something, using the services, cognitive services we have. There were a few sessions yesterday, I think, and one of the speakers, Adam, was covering cognitive services. But there's a lot of things you could do with them, and they actually helped me a lot in my little journey. And I want to show you a little example and little demo using custom vision service, and some of you may have seen that or tried it yourselves, of how I actually can build a little model using that. So I hope you would be able to see the video. So basically, for those of you who haven't tried it, so there's a customvision.ai, and I'm sorry, it's going to be a little bit small on that screen. Basically, I can go to that service, I can create a new project. I'll have some sample data set where I have a number of ponies. About 15 images would be enough for each of the class of ponies. And then I've add those images. And there's a bit of a lag here. So I'm adding the images, which you can't see using the Explorer, but I'm adding 3 classes. There would be one called Applejack. Many of you know that one? Yeah? Right, so there would be Applejack. There would be Twilight Sparkle, I believe, the next one. And the Rainbow Dash. Let's just see it coming a bit slower. Yeah, so there's a rainbow dash coming in. So I can add the image, bunch of images, say, well, this is the tag. Model will take it in, and then I can, let me just see if it's the third one coming up. Yeah, it's a little bit slower. So the third one is coming up, so the Twilight Sparkle. And so once those images are uploaded, and again, I have about 15 images each for each of the class, I can go and train that model using these images. And that will take a few seconds to train, and you can see it on the screen happening. It's about 20, 30 seconds. Take the data in using the pre-built models, which Microsoft has provided you at the service. And at the end of this training, you have a fairly precise model which can actually recognize those 3 classes. And there would be, I'll show you a quick test as well. While that model is there, so I can take an image from just a website, or I can take an image from my local machine. And this is what I'm going to do here. And again, you can't see it selecting me on the Explorer, unfortunately. Sorry, the screen share. But then I've selected one, and you can see there was a tag. Let me just kind of pause here for a second. So you can see there is a image of the pony it hasn't seen before, and there is a tag associated with it, very high accuracy. It's an Applejack. So this is cool. So I've trained my model, but what can I actually do with that? Can I now use it in some way, shape, or form? We are developers here. We want to expose it to the services. I have REST API endpoint, which I can use now. So the service allows you to do that too. And you can publish the model, and you publish that training of that iteration. And you will get a prediction URL, which is, again, it's a little bit small, but if you go and try it yourself, you'll see you have a URL, you have a key, and you have a body, which you need to pass, which would be either URL of the image or the image itself in the byte form. And after that, you can go and use it within your website, integrate this REST API endpoint and do whatever you want to do with these little points. Another option, and here I'm showing, is you can actually choose a compact form of the model. That means that you can now take it, once you train it again, you can actually take it and export it and use it in your mobile applications. And let me just scroll it down. So you need to retrain it. I'll skip this step a little bit. And once you're done retraining, you can, come on, yeah. So you can go and export the model. And you see there's a few platforms you can export it to. So you can export to your, if you're building iOS application, if you have an Android application, Onyx format, Docker file. So there's lots of ways how you could actually reuse it later on your edge device, and you actually won't need internet connection for that. So that would be your, your intelligent edge as a device using this particular model. So this is all fun. And what I did build actually is a little iOS application, again, reusing the CoreML app. And now I have a little app on my phone which says, okay, is this lunchbox has my daughter's favorite pony? Yes or no? And then if it's no, I should actually go and buy another one because her favorite is Rainbow Dash, and I'll be damned if I buy the other one, right? So this kind of things you could do. But this is all good. So this is very easy. Few minutes, you can actually build your own models given you have your data. Cool, problem solved. But obviously, we're not here to see all the shiny tools which do everything, all the magic for us. So we are here to see what is actually behind the scenes. So how do I build something similar? How do I actually, what is behind the scenes? What's under the bonnet there? So let's review the basics. And there are a few sessions yesterday and today around neural networks. So there might be some repeatability here. So sorry for that. But basics are important. So many of you have seen the variation of this. What is AI, what is machine learning, what is deep learning. So in case you have any questions about this is a very quick one. So AI overall mimics human behavior, any senses, hearing, whatever you can think of what humans can do, those cognitive abilities. This is all under the banner of AI. Machine learning is a part of that. Machine learning, and there are different ways, different things what machine learning can do. The main thing is it can do pattern recognition on the data, whether it's numerical data or any other type of data. So this is more important. And then deep learning is just a subset of that, where it uses neural networks, specific types of algorithms to actually do this pattern recognition on specific subsets of problems. And we'll talk about the vision problem is one of them. It could be a speech. It could be some other problems which deep learning can now solve. If you want a quicker differentiation, a colleague at Microsoft put it like this. So if it's written in Python, it's probably machine learning. If it's written in PowerPoint, it's most likely to be AI. Right, let's talk about machine learning first. So one important thing about machine learning is feature engineering. And imagine I have asked you, I have a problem. So I have thousands of images of clock face, and I need you to help me to actually understand which hour is it and what minute, what hour hand shows, what minute hand shows. And if we are all equipped with machine learning knowledge, and after the session you will all be, you say, okay, now I have images, I can do some clever stuff about it. But actually, if you have a bit of if you have developer knowledge, you're like, okay, maybe I don't need to know too much about this data, but maybe I can just track the the tip point of the hand and start understanding the X and Y coordinates and see where they are location-wise, and maybe I can do some clever stuff around it. Also, if you have a bit more domain knowledge of what actually clock shows you, maybe you can now translate those X and Y coordinates into angles, and then all you actually care, so each hour will have its own angle, each minute will have its own angle, and then essentially the problem is boiling down to which angle on the picture it is, and then I can find it out. And this is where you are basically going from a bigger problem of thousands of images of clock faces into angles. And this is your features, which are very important for this particular problem. But then the question is, do I really need to have machine learning for that? Because essentially what we're coming down to is we can calculate the angle, and we have a number of lookups, dictionaries, and all of that, a few lines of Python, and you're actually done. So there's no need for machine learning here. And there was a previous talk, I don't know if any of you attended, by Tess, just a previous one, and she was talking about you don't always need machine learning for things, right? You need to understand what is actually the problem is. So maybe it doesn't have to be machine learning. So this is where I want to you to take away as well. So sometimes you go to the feature engineering piece and maybe there's some simpler old school method which will help you to deal with that. But sometimes they're not, and then you actually need to go all the way in. If we talk about machine learning and deep learning, so there are two differences how it works. So in traditional, or sometimes people use shallow machine learning, is you get some input, and in our case we have images of the car, and this is how we used to do image recognition before the deep learning algorithms were working the way they are now. And you need to do this feature extraction. You need to do a bit of smart things before you can do any, building any algorithms. And that is actually most of the work of machine learning, of data science and machine learning experts actually spent in the space of data transformation, data preparation, and get to the point where you can now pass it to the algorithms to do classification or, depending on the task, some kind of machine learning algorithms, which will give you an output. In our case, it's a classification, yes, no, is it a car or not. In deep learning, and just the way things are, is it allows you to do automatically. It learns about the inputs and extracts the features as part of that learning. So that's why it's all combined, but that's why you need to have lots and lots of data to actually learn from the images and extract those features. And that's a very important distinction. What do these deep learning networks actually learn? So they learn things called representations. And the way the learning is done, and it's a lot of data and a lot of passes on the same data until we learn something. And if you look at this picture, and I believe it's somewhere in the north of Norway, so if we human look at this picture, so it's a kind of bridge/road, somewhere there's a water, it's a very nice landscape. So when the machine learning, the deep learning networks will start learning this image, so it might pick up first some edges, it might pick up some textures and patterns on the first runs. And then next one would be, okay, there might be some, parts of the kind of horizontal lines, vertical lines, some other shapes, bigger shapes. And that would be our mid features. So the first one were low-level features. This would be middle-level features. And then altogether, they can actually construct those mid-level features into something more meaningful, like there's a bridge, there is a leg of the bridge, there is a part of the road, etc. So this kind of things will be called representation. This is what deep learning networks actually learn on those sets of data. And we'll get back to that as well later on. So if we talk about images, so what is an image, right? So I have an image of one of the ponies. So actually, if we talk about software engineering here, so each image can be, looked at a different color channel. So there will be red, green, blue. And each of the image will also have a certain height and width. So all of this information, and then the intensity of each of the pixels there. So this is essentially our wonderful pony image will be shown something like this, where you have each of those pixels, highlighted or not, and there would be width and height. Again, when we talk about machine learning, it's all about numbers. So we need to have our images, our text, our whatever the input is, translated into that numeric format of some sort of shape. So this is how our inputs would be: pixels, heights, and width. So this would be that input. So now let's deep dive a little bit more into the neural networks. And what is that unit of the neural network? So what is the neuron? So neuron is they say it's biologically inspired, so this is what we use, we have in our brain. So the kind of ideas that there would be some input, there would be some weight associated with the particular parts of the input coming in. So for instance, here's a very bright light on those corners, and it's quite distracting, but here I can't see much. So there would be a lot of, input coming from those sides, and there would be a lot of weight associated with it in my brain now. And then there is a certain bias, and in this particular case, for each of the input and weight, we will multiply this, and then we will make a sum out of it. There will be summation function, which will be then offset by a bias value, which is bring some nonlinearity there. And then we will also have at the end of that summation, we will have a gate, and we call it activation function. We will decide, will this signal actually pass on further on or not? So this would be nonlinear function. We'll look at this a little bit more in detail. But this is essentially all the kinds of calculations happens in the neural networks, and that happens millions of times. So you have your X as inputs, W's are weights, which is multiplied by on the input bias and activation function. And each of the network will consist of a number of layers, and some of them, they have very specific roles. So there is an input layer, you have it here as X, and there would be an output layer as Y. And in the middle, you might have one layer, which would be your shallow neural network, which is a very simple neural network, only one layer, which is hidden, and all it does, it just does the calculations. Or you might have a deep neural network, and deep in this case will just have number of layers more than one. This is all the magic there. But those layers will do a lot of calculations, and again, think of each of these round dots is actually doing that calculations, which you can't see, just it's on the top of the slide, but it's basically doing all of that stuff. So this is the layers. And as I spoke about activation functions, again, think of it as a gateway, whether the signal passes on or not. And it really depends on the where in the layer we're doing these activations. So if we're doing it within the hidden layer, where we're just passing the signal from the input to calculate the output, so there are traditionally we use three functions. So one of them is sigmoid, there's a tanh, and then rectified linear unit, which is one of the most popular actually right now. And the idea, those activation functions should be easy to compute, because we're going to do a lot of those calculations, and you'll see again in the demo in a moment, how many calculations we actually need to do. So we take, we'll take the derivatives of those functions for calculations, so it should be easy to compute as well. They should be continuous and infinite and monotonous. So it's kind of, there's a few properties around this function. That's why these three are often used. And rectified linear unit is basically, if anything is negative, we don't care. We are not going to pass that image or the signal. If it's higher than 0, then we're going to pass that value as it is. If we talk about the outer layer, output layer, so this is where we actually calculate the result, is we have, again, we might use three options there. So one, if we actually, our calculations about the numbers as an input, and we want to have an output as a, as a number as well, so we actually don't do any activation, because we just calculate it. And think about house prices, etc., when you have a number as a starting point. If you have, in our example of classifying ponies, when you have a different classes of what we want to achieve, at the end of it, we want to say, well, is this twilight sparkle, is this rainbow dash, etc., then we want to have an answer saying which one of these images actually have a particular probability. And this is where we're going to use a softmax function. Again, it's one of those functions which can be computed efficiently. Or there is another one which is called sigmoid, and often used for unrelated probabilities. So there are lots of functions, and you will see how that could actually come together. The last thing is the essence of why deep learning actually works and how things are learned over the time, is the idea of backpropagation. And there's a link to the nice blog article, goes in length of how things are done. But essentially, when we start learning, we will think of those weights and bias. We don't know, actually. So we have an image. We don't really know anything about it. We're going to learn from that. So we're going to initiate them with some random values for the start. And as our learning starts, we do calculation on each of the layers. We do get to some output. And then, because we have enough sample data, we have training data, we actually know what the output should be. And then we compare, did we actually achieve what we needed? And if it's not, we understand what would be the difference, what's the error between what we expected to see and what we got. And we need to propagate that error value, that back to the start, and that's done through the derivatives, through this backpropagation algorithm. So we kind of start fine-tuning those parameters, the weights, the bias, and so on, which will, on a number of learning cycles, you will actually get to the point where we now find what are the right parameters for our network to work on our data. So, but again, look at the website, and the slides will be available as well later, so if you want to take a look. And last thing on the networks as it is the different architectures. because you can connect those layers in a different ways. So one of them, and is the most simple one, is densely connected neural networks. We'll look at this in a moment. So it's basically everything is connected with everything. Convolutional neural networks is a separate type of networks which it works very well for the input, where you have some spatial relationship, and vision images is one of those, because there's a lot of patterns around each of the pixels, so you can't have just red and blue pixel randomly. It's quite often you have some kind of relationship there. And then there's another type of neural networks, just for knowledge, it's recurrent neural networks, which deals very well with the time relationships, so time series, language, speech recognition, etc. If you want to use it, get your hands dirty, how do you actually put this into practice? So there are lots of frameworks. I'm sure you're familiar with at least some of them, or heard the names. So TensorFlow, MXNext, Caffe, PyTorch, Keras, etc. Lots of frameworks right now available in the industry. Lots of tutorials and materials online. What I'm going to use for the demonstration today is Keras, which is a high-level abstraction of on the top of TensorFlow and Caffe, etc. And the idea is that it enables you to build things very quickly, and it's quite readable code as well, as you'll see. So with that, I just want to show you a quick demo on, first of all, on those densely connected neural networks. So how do we actually build those models? And again, as I mentioned, so in this particular case, you have all the neurons are connected in all the layers, as you see in the picture. And that's why we'll have a big number of calculations to be done within the process. And there's a certain characteristics of each model is how many parameters it actually needs to learn from that. Let me just switch to the... OK, yeah, you can see that. So I'm using, for the demo, I'm using data science virtual machine on Azure, which can come with a GPU processor, and you can do all this stuff there. So in my case, so for the first demo, I have a number of images. And again, remember this height and width of the image, 224, 224. I've got 3 colors, so I have 3 channels. I could have had just one grayscale, so it would be 1 channel only. And so you can see my input size calculated, and my input shape is also being just set up as it is. It's in Python. And this is basically, so this part, cell number 2, is we do import Keras. So this is what we do for do any deep learning using Keras. We specify that we're going to have a sequential model. So we have a number of layers going one after another. And we're only going to use dense layers in our case. That means all the neurons will be connected to each other. And all we do here is kind of put the scaffolding hole. This is how my model should be. So I have a sequential model. It has the first one will have, it will take an input of this particular input size, which I've already calculated, of this input shape. It will use the activation function relu at the end of this layer. And it will have 128 neurons in this particular layer. The next layer, I chose to have same relu function, and it will only have 64 units in the layer, 32, and then the last layer will be number of classes, so 3 classes I have in this case, and I'll have an activation function softmax. And that's, I declare this is what my model will be. And again, so this, if I run the summary of what exactly it will be and how many parameters, and this is where I want to show you how many parameters will be in this case. So you can see the total number of parameters is 19 million in this case. So it's 19 million calculations for each of the training will be happening for this neural network. And how it is calculated, so I kind of gave a little bit of math. So you have the shape, you have 3 channels at the first layer, then you have the number of neurons, and you've got a number of those bias values, so you already have 19 million and a bit. And then for the next layer, slightly less, you have 128 input from the previous layer, you have 64 neurons in this layer, multiplied together, have bias, 8,000, and so on and so on and so forth. So this is how it will work. So with that, let me just switch to this quickly. So one of the tutorials, and if you're going to start and looking actually at neural networks from scratch, is MNIST database. And this is a understanding, I have a database of handwritten digits, number of training and testing images. I think its dataset come from the US Post Office. And, can you identify what did I roll? So there are lots of samples. You can see it yourself on Keras, on any other framework. So I won't go into code here. But what I want to show you, it's a nice visualization. Where was it? Here? No. This one. Oh, I lost it now. Right. So there's a 3D visualization. And I'm going to write number here, but before that, so there is again, think of that densely connected network. So this is my input space at the bottom. Sorry, you probably don't see it very well on the screen, but then there is a layer number 1, the hidden layer number 1, which will have a number of neurons. Again, think of those 128 neurons, for instance. There will be a second layer, 64 neurons, 32, whatever it might be, and then the output of that network. What is it expecting to actually see? And you'll see some of the neurons firing up as it believes what it should be. So for instance, if I did 3, you see there's certain, because the neural network trained and learned that number 3 will fire specific neurons, which will provide that signal further on the first layer and from the second one, and will maybe not fire some of those. So activation function will not work there. Then it will come to 3. If you do some other number, let's say 7, yeah, so you can see, so downsampled. So the first guess is 7, the second one is 5. So it's kind of fun to play with. So this is how you can visualize what actually happens in this particular case. Oftentimes, it's actually quite hard to visualize what exactly is the neural network is learning. There's some kind of research papers and frameworks and libraries to show you what is actually that part is learning. What are the low-level features, mid-level features, and high-level features it learns. If you think of number 2, so there might be some kind of ending at the end. If it's 0, so there would be a circle, whatever it might be learning. So it's kind of interesting to see. So you see that's here, for instance, I think it's 2. Second guess, maybe 8, because it's probably close enough. So this kind of things is there too. Right, so that is MNIST. So that, again, there's a link if you want to play with that. So what we focus for the rest of the session is the convolutional neural networks, because they are the ones which are to be used for the image classification. Like I mentioned, the biological inspiration is, we have visual cortex, and, our cells are sensitive to certain areas, and how we could actually use the kind of abstraction of that in the deep neural networks. Important part, spatial relationship and kind of repeated patterns there, and some sort of structure to the image. So the standard architecture layers for the CNNs, they're usually abbreviated to, are you have a certain parts of the architecture which is actually repeated, but there are certain layers, so they do different things, and they have different focus. And the convolution layer, there's a pooling layer, and there is a fully connected or dense layer, as we already spoke about, which then will lead to some output. So if we look at in more detail what each of those types of layers do, so you will have, first one is convolution layer. So this is where the name comes from for the CNNs. So imagine you have an image, and we look at this point, just kind of imagine we have a grayscale, so we only have one channel. And, mentally imagine you have a torch, and you actually go row by row, column by column, and the image, and you're trying to highlight what is important in that image. And think of that bridge representation slide I've showed you. So what we will learn there, if it's, bridge, so you have some maybe horizontal features, some vertical edges, texture shapes on the first runs, we'll run those. So we'll start extracting this, deriving that information from the input. And those filters, those torches are usually quite a small size. So you have 3 to 3, 5 to 5 usually being used. And you start building that feature map. So what is important? And this is what convolved feature is there. So essentially, we're going from a larger size of image, we're going to a slightly smaller one, where we have highlighted something very important. And there might be different filters. There might be edges, there might be horizontal, some kind of angles, etc. So what we're trying to derive there. And you might have 10, 15 layers or filters of that. So you'll have 10, 15 layers in this case, which will then feed into the results of that. Those calculations will feed into the pooling layer. And pooling layer has one specific purpose. So the idea is that you want to reduce the dimension. So we still talk about, even if we start with images of 150 and 150, you might reduce it a little bit, but we still talk about big images. So a lot of calculations, a lot of parameters to calculate again and again. So pooling layer will start kind of reducing that dimensionality, but we still keep the important information there. So we try not to lose as much of information as we can. And again, you have a smaller filters in this case. So you will be the strides of, let's say, 2 by 2, and you can see in the red sort of red area there, it will be then calculated what is the maximum value there, or what is the average value there. So depending on the different ways how you could calculate, but one of those is maximum value. And then it will then go from the matrix, in this particular case 8 by 8, into the matrix of 2 by 2. So we kind of reduced the dimensionality, but we've retained the important parts about each of the areas. And again, think of that spatial relationship in the image, very important. That's how we can actually do this without losing a lot of information. And again, you will have a number of those layers in the network, and then you will repeat. So you'll have another number of convolution layers and another number of pooling layers. All of that does one important thing, is that distillation of the information. If I were asked to all of you to draw a picture of a bicycle for me, so all of you will have, kind of maybe something, you'll have 2 wheels, you'll have a saddle, you have but there would be some other additional elements. But at the end, whatever the images of the bicycles are, it will come down to the pretty much very similar picture on your right. So this is what the CNNs will learn as well. Given the millions of images I might be given, well, in Pony World, maybe not millions, hundreds. What is important about Rainbow Dash? What is important about Applejack, etc.? So you will distill that information. And then the last 1 or 2 layers, usually you would have those fully connected dense layers, where you will have all of that knowledge of those low-level, mid-level, high-level features. And then you want to say, well, what is it actually the output should be? Given my image at the start with the previous layers, which of the ponies in my example it should be? So I have whatever the input was, I have the example, the output would be Rainbow Dash with a probability of 0.84, so quite, in this particular case, quite high up. Or it might be still second best probability might be 0.1 of something else, Twilight Sparkle. So this is where you get as an output of the CNN network. So let's build it. Let's see an example how you actually do that. So as I mentioned, you need data. So I have found the fandom website where they have lots of images of My Little Ponies, knock yourself out, lots of others. And there's also a nice script which allows you to actually pull the data from Google Images if you want to. So what I'm going to do here in this demo, so we're going to use this custom classifier. You have an input, so I have 3 classes of images, 150 pixels each on the dimensions, and the output is 3 classes naturally, and the names to be predicted in this case. Right, let me switch. So all of that image samples and the notebooks also on my GitHub, which I'll share with you later on. Let's start here. Right, so data. Right, again, we use Keras, as I mentioned before. We build the model. So you've seen an example of how that model can be described. So in our case, for the pony image classifier, you'll have a little bit of a different setup. So you'll still have a sequential model. We still have layer by layer. But then you'll have different types of layers. And we will have convolutional layers with, again, activation function, input shape, and the kind of the shape of the filter I want to use in this case. You'll have a max pooling layer, so pooling layers which will use max functions to condense that information. And again, there will be convolutional and pooling layers on my data. And then at the end, what we're going to do, we're going to take all of those outputs from the last layer. We will flatten it out, so all of the inputs of the previous layers, and then we will start connecting them with the next fully connected dense layer and the last one, which will actually give us the output of our class, 3 classes, sorry, using the softmax activation. And if you want to see the summary, again, it's, there's a number of parameters we're learning. So it's not as crazy as in case of dense layer I've showed you just before. So it's have about 2 million parameters. So when we specify the structure of the model, now we want to say, well, when we're going to use this model to learn, what is our way to measure the error, and what are we actually learning there? So if we using example of 3 classes as an output, so we actually have a categories what we're trying to predict. So we're using categorical cross entropy as a loss function. And if we do a numeric calculation, so there would be another one here. And in our case, our metrics would be how accurate are we in predicting what we actually trying to predict in our examples of images. We spoke about this, so obviously images, we want to take them, whether they're JPEGs, PNG files, etc. So we need to get a number as an input for the network. So we're going to do a bit of data pre-processing here. So Keras comes with some pre-processing libraries already, so you can actually, it's called image data generator. So we'll have our training directory and we'll have our validation directory. So validation directory will be used for training data will be used to train the model. Validation will be used to check actually how well are we performing on something we haven't seen before. So we haven't just learned everything, but we want to generalize those models. And so we start building those image data generator classes. So we have, rescaling them. I'll talk about this, some of the things you can also do when you have a small number of samples like I do. So you might be stretching them a bit, you might be rescaling them, you might be twisting and turning them a little bit to get more data for the networks. We'll do some things here. And then essentially what we say, our train generator will have the size of, the shape of the file would be 150 by 150, and the class mode is categorical. And we will use it in a batches of 16 images per for the training. And you can see I have about 250 or 220 images belonging to 3 classes in the training set, and I have 80 images for the validation. The next couple of things I'm using it later on, so I'm just getting the names of the classes, so you can ignore that. And this is basically how you train the model, the one we've described before, given the metrics we want to achieve. We say, well, take the model, feed the generator, which we've already discussed, what the images are coming in, and we're going to train it 7 times, so 7 epochs, using use the validation data set and use the steps, and actually just using those images to calculate how close are we predicting. And it runs, so I wouldn't run it now, but it runs about a few minutes here in this particular case on the images. And for the image classification, you want to use GPUs, because otherwise CPUs just wouldn't be enough, or it will take very long time. But you can see our metric of how good our model was accuracy, and unfortunately it kind of broke this down in 2 lines, but we started with the random values at the very first training, at the very first start, and accuracy is 0.49, which is basically a guess completely. It's kind of crap metric to have for this. But then because we did the first run, we've learned that we're quite far off, and then we started backpropagating that, that knowledge back, and we started doing some modification within the network, within the weights and biases, and we started improving our accuracy quite a bit on our training data, and which is cool. So we actually, on our trained data, we've achieved accuracy of 0.92, which is awesome, but we actually basically just learned those images very well, right? This is what happens there. The most important metric would be actually accuracy of the validation set, testing set is, at this point, at the end of it, it's still quite high up, but it's it's lower than the training set, and this would be the most important metric for us in our case, actually. So because this is how the model performs on data it hasn't seen before, so how well it does. We can save this model to use it later. We can do some plots to actually see what was the changes of this training and validation accuracy, and similar to how it actually converges and maybe changes. So I have a few, just 7 epochs. I might have had 20, and you might see that at some point it converges, but then it actually completely goes away. So model actually doesn't learn much. So maybe you want to have less learning. So there's different ways how you can interpret this and act on these results. And same with the validation, with the loss, with the error we get. And actually, again, same, think about at the start when I did this custom vision, when we trained the model, but how we can actually use it for data we haven't seen, how we test it. So we can take again our model, and I wrote a little function here. So predicting, given an image URL, and images are in this case in the blob storage, use the model and just predict this particular image, what would be the probability of a particular class in my scenario from 3 ponies there. Yeah, and then just basically for all the images in the folder, I just do that. And you can see the example here, which I ran, I think, yesterday, is we had a processing image, Applejack, and the prediction class was Applejack, quite high up. So I have to say Applejack was quite easy to, I mean, it's easy to learn because it's a very distinct pony. It's yellow. It's kind of, there's lots of features which is for humans very easy to remember. When it's coming to those where there's Rainbow Dash, Twilight Sparkle, they're kind of similar or colorful and all that, you have that model actually still predicts it, but the score, the predictions are quite low. So it's actually at the margin of errors. We can still take it as the highest probability of which of the probabilities is the highest. And we can say, well, this is likely to be this particular pony. But actually, as you see the numbers, the score is quite low. But you can see for all of them, it actually predicted them correctly in some way, that the top probability was the right one. So this is how you actually build those classifiers. And again, with Keras, you can export it as a, you already have a model. So I do have it as a, as a file. You can import into your mobile application, onto your drone, onto whatever, whatever you're working with or want to explore. So there's a lots of ways how you can then use it. So this is the consuming of that models. Right. I hope you're all now excited and thinking, okay, what can I build now? So a few things I want to identify as well and talk about just a little bit outside of the world of ponies is the issues with, in the world of deep learning. And there are 2 issues usually, the main ones at least. So one of them is, we already highlighted, so small data problems. So we might not have enough data to train on. So you've seen that in my scenario, so those 2 classes, Twilight Sparkle and Rainbow Dash, were identified, but just about. And it's literally down to the fact that I don't have enough images. I have only maybe 50, 60 images per class. You want to, if you don't have any, if you start on this path, you need to have tens and thousands of images, or you might have some other techniques which we'll talk about, but it's a lot of data required. And if you have small data, so that you need to do something smart about it, where you can actually squeeze a bit more information out of the small data set you have. Overfitting is another problem where basically, so any machine learning model can suffer from it. It's not just deep learning issue, it's traditional machine learning as well. And the idea is that model can learn what you give, just rote memorization. If 90% of my data shows something will happen and 10% says something will not happen, I'd be 90% correct if I just don't even say anything. I'll just say, well, it will always happen, and because it's 90% does it, right? So you just learn rotten, memorization here, because model will adjust the best on the training data to show the best performance. And that's why you remember that training accuracy versus validation accuracy is important. However, what we're interested when we build those models is, could we use it for our general data? So how well will our model perform on the data it hasn't seen before, whether it's images or numeric data? And this is where those validation sets and all other techniques are very important. As I mentioned, more training data often helps to reduce the pure memorization here. An additional techniques for the small data issue is data augmentation, or essentially squeeze more training samples from your existing data set. And that, in this way, you can do random transformation with your existing data. So you can squeeze it, stretch it, rotate it, so that machine learning models, the deep learning networks, they actually learn not just from that one image you have, but you might actually generate 50 similar close enough images out of it, which will then be used as a part of the training for your model. So that's one of the ways to do it. Second way is actually modifying the way the neural networks learn. Again, the example here is on the left-hand side, you have densely connected networks. So you have all the units are connected there. And then you might want to bring in that dropout or actually switch off some of those neurons to actually see, does model actually learn something important? Does it actually can still propagate that signal back to the output in a reasonable rate? And you might get reduction of your accuracy in this case, but you might still get good results. And that means your model actually learns from less, and you have less computation, and actually it can again generalize much better. So that's another technique which learns what is important actually in the input. Another way how things could be done in the deep learning is you might actually stand on the shoulders of giants. You might actually use what Microsoft, Google, Facebook, all the research academia, done already in this world. So they already built some amazing neural networks to solve challenges. One of them is ImageNet, when you have millions of images and hundreds of classes. They've already solved that problem. They have the way to do it. They don't have it for my ponies, but I can actually use most of the architectures because they're already learning stuff from the images, and I can then transfer that knowledge for my own specific business problem. And the idea is that you take the pre-trained neural network, and for example, trained on ImageNet is a kind of de facto standard now, and then bring my own data, do a little bit of tweaking there on the existing architecture, and then have my own pony classifier with all the amazing knowledge and the research backed up for my classifier. And how you do it technically is basically, you can see on the left-hand side you have a trained convolutional base, and you have that output layer, which is actually a classifier, as you remember, that fully connected layer, which gives me the output. Well, if you take ImageNet, when it can describe what is in the image, is it boat, bridge, whatever, so I can actually discard that particular last one or two layers and replace it with my classifier, what actually I'm expecting that to be. And that would be then given the results on my data then. And how you do it in Keras, it's a little bit small maybe, but essentially you do, when you create a model, you say, well, create a model the way we did it, so say it's a sequential model, but the first layer would be the convolutional base. And that convolutional base will be one of the existing models. And there are quite a few of those network architectures you can find. Exception, VGG16, etc. There are plenty of those available. And again, Keras comes with a lot of this already out of the box. And you say, use that convolutional base. The only thing is, do not include the top layer, the last layer, because I'm going to be doing something about it. And in your model, then you say, well, after I have this convolutional base at the start, then take additional 1 or 2 layers when I'm actually using it for my classifier. So that's how it's done in the code. And then you can go further down inside the network if you want to tweak some other layers, which is kind of not the output ones, so not close to the output, but a bit further in. You can again do some fine-tuning and tweaking if you really need to. So there's lots of ways how you could use what you have, what has been already created for you, and tweak it. And just a last demo I want to show you is how we could use these pre-trained models for air classification tasks. And when I have a number of my own personal images and I'm using the existing pre-trained model with the changed output layer. And so the transfer learning. So if you can see, so I'm using a VGG16 model, which has been trained on ImageNet, on all of the data. So this is my convolutional base. And if you see, so this is something has been done before, and you can see how many layers it actually has. So like, oh, scroll and scroll and scroll. Some of these networks can have hundreds of layers, so it's kind of, that's a small one, apparently. So you can see how many parameters actually trained there, which is quite a big number. Anyway, so this hasn't done by me. That has been done by smart people there. And then I'm doing the same. I'm taking my own images. I think I'm declaring the model a bit later. And taking the images just to, sorry, hold on. Did I skip that bit? Sorry. I think that the last bit I was convolution-based summary, sorry. Yeah, I'm actually in this particular scenario, I'm just taking that convolution base, I'm using it as it is. So I'm actually not doing any additional learning on it. I'm just trying to see how it will use, how it will be done in my, on my images. So that's why I'm taking my number of personal images, and all I'm doing is predicting an image given the model, given the convolutional base model, and just given the results, how well it predicts particular images. And I'll just show you the more of images. So there's a picture of Tower Bridge, and you can see it. So the answer is it's suspension bridge with quite strong probability, and then I had some gin and tonic in this glass, and says it's a beer glass, which it is. And if you want to extend it to more classic, your own classifier, your own outputs, then you actually start building on the top of that convolutional base. Cool. So takeaways, I guess, from this session, as if you just want to look at the, build quickly your classifiers and have an API, so what you're interested is actually building those, APIs, how you could use them. Take a look at custom vision services if you haven't seen, it's pretty cool. And we use behind the scenes there's a lot of transfer learning and all that, so you actually don't need a lot of data, so it does a lot of smart things there. If you want to build your own classifier, you want to get your hands dirty with the code and keras, etc. So have a good data set to work with, so quite a lot of data. Use keras or TensorFlow or any other framework you feel like. Most likely you'd need to use GPUs, so either have it your own or use the cloud. With the specifics to convolutional neural networks, so you might start from scratch so they actually understand what's happening behind the scenes and how you'll see how long it might take to train it, etc. Or you might use pre-trained models. Use the data augmentation techniques. Use dropout layers. Oh, what happened here? I think I might have touched this one. Sorry. Okay. Sorry about that. Resources, some really good books and online courses. So deep learning with Python is one of the best ones in red. So that's written by the author who created keras libraries. So it's really cool. It goes very well in explanation of how it works. Grok in deep learning is really good as well. It's less math and a bit more of kind of concepts, etc. And fast.ai is a really good online source for understanding how deep learning works. And so what's next for me? Obviously, my daughter is growing, so a bit more. I don't know. So thank you so much for your time. And if you want to have the resources, find it on GitHub. Thank you. So we have a few minutes if you want questions. I'll be here anyway, just packing up.